So in this video we'll be going over acid strength and acid ionization. So before we begin, let's ask ourselves, how is the strength of an electrolyte determined? And it turns out that it's determined by the dissociation of the electrolyte into its component ions in the solution. What does this mean exactly? Well, let's say we have the following, where if an acid is strong, then it will reach full ionization. Otherwise, if it's weak, it will reach partial ionization. So what does this mean exactly, chemical-wise? Well, let's say we have this pseudo equation right here. What do you notice? Well, you'll notice that we have a Bronsted-Lowry definition of an acid-base system. You'll see that HA is an acid and it has its respective conjugate base. But pay attention to the arrow. Why is it a single arrow? Well, HA is a strong acid, and because it's a strong acid, it reaches full ionization. And when that acid reaches a full ionization, that acid breaks into its individual components, and when a reaction occurs, there's no more of that original reactant. Now, I've only showed you the pseudo equation, but let's say we were to employ an actual equation. And hydrochloric acid is a strong acid, by the way. So, yeah, you'll notice that strong acids will break apart to its individual ions. And when dealing with strong acids, there are 6 that you have to commit to memory. And out of the 6, can you point out which one of them is out of the ordinary? And if you were to say that sulfuric acid contains one more proton than the rest, you'd be correct. That one is unique in a sense that it has one extra disposable ion. And we call that a ditropic acid. And if that acid happens to have 3 or more protons, we just call it polytropic. So we got the concept of strong acids covered. And what about weak acids? So let's say I'll have hydrofluoric acid, and it underwent hydrolysis. And why am I drawing double arrows? As I've said before, weak acids tend to reach partial ionization. And as a result, the hydrofluoric acid, some parts of it remains unionized. And while it does follow the general pattern of the proton donor and proton acceptance trend, it's still a weak acid. So we get H3O plus and F minus. Okay. So an HF solution would still be present, whether it's ionized or unionized, and hydronium and the F minus ions will be present. So what does this mean exactly? It simply means that if you were to have a 1 molarity hydrofluoric acid solution, that would imply that the hydronium would have to be less than 1 molarity because some of its molecules ionize to form hydronium. Now, earlier, I used an example with hydrofluoric acid. If I have hydrochloric acid and it underwent hydrolysis. We know that it reaches full ionization, correct? H3O plus and Cl minus. When that reaction reaches full ionization, and I was to provide the concentration of hydrochloric acid, would you be able to already know the concentration of hydronium? And it turns out you do, because it's full ionization. When the reaction occurs, there's no more of that hydrochloric acid. That 1 molarity hydrochloric acid has a 1-to-1 relationship with hydronium. And that's just something that you gotta keep in mind when dealing with strong acids and their weak counterpart. So, in general, the stronger the acid, the weaker the conjugate base, and vice versa. Okay, so we got that out of the way. Now, what if we were to deal with finding the acid ionization constant? It turns out that, especially for weak acids, you have to do a little bit of some thinking, basically. So let's say we have HFA, and it was to react with water. And HFAs are a weak base. Okay, so we know that HFA is a weak base, and when it comes to finding the equilibrium constant, it's usually the products or reactants. Now, we have 4 species in this acid-base system, but only 3 of them will actually make it into the equilibrium constant. And it turns out water will be omitted because solids and liquids are negated when solving for the equilibrium constant. So therefore, K of A is simply H3O plus times A minus over H of A. And well, you can write hydronium as H plus. They are used interchangeably, and this equation gives us something to think about. If K of A was greater than 1, what would that imply? Well, we have the products in the numerator, and if Ka is greater than 1, that would mean that the acid-base system is product favored. Now, what if it's less than 1? That would imply that the reactants are of a greater magnitude compared to the products. And as a result, the acid-base system would be reactant favored. That's just something to think about. Now, we got the conceptual part down. Let's do some thinking here. So say we have hydrofluoric acid, and its equilibrium constant is 3.5 times 10 to negative 4th. And we also have HClO, where its equilibrium constant is 2.9 times 10 to negative 8th. And the question is, which of the two has a stronger conjugate base? Do keep in mind that the strength of an acid is inversely proportional to the strength of its conjugate base. So the stronger the acid, the weaker the base. And given that logic, would have to be HClO, because it has a really weak acid. Pay attention to the -8, 10 to -8. It's really small compared to 10 to -4th. And because the acid is really weak, and because acid strength is inversely proportional to the strength of the conjugate base, HCl would have to have, well, the stronger conjugate base. And that should cover acid strength and ionization. This is just a conceptual part. We will do numerical problems, especially involving ice baths, assumptions, and yeah, that's pretty much it. And then there's pH, but that's for later in the videos, because in order to approach more nuanced, math-heavy concepts, you have to understand the behind the scenes of the rationale when approaching these problems. Alright, that's it. See ya.